Okay, I see that people are joining. Sorry for inconvenience, folks. Can you confirm if you can see and hear me well now? You can just type in the chat. Okay, great. I will just give 1 or 2 minutes for others to join us. The link has changed. Yeah, until while we're waiting, I will just give a couple of organizational moments. That's a YouTube stream, so it is automatically saved, so you can replay it anytime you want, and it will be available afterwards, of course. You have a chat. It is detachable, so you can leave your comments or questions there. I can't promise we'll have enough time to answer them all, but anyway, you can join the All Robotics chat in our Slack, and I can answer them there. Okay. I guess we can get started, and well, the others will join, and they can start watching the stream from the very beginning. So welcome everyone on this quick intro to robotics tech talk. Well, just a couple of words about myself. My name is Harry Korol, Principal Engineer and Automation Competence Lead at Waverly, Ukraine. I'm currently leading one of our internal projects related to robotics. I would probably demo it in the middle of this session. I also participated in one of the commercial projects that we had about 1 year ago, where we successfully won the pre-sale campaign and completed the POC phase. Unfortunately, the main development is currently on hold, but I would like to take an advantage of this time and to involve more people into the robotics learning process. It is quite exciting and challenging at the same time. Yeah, so we have a lot to cover. Within this session, you will see a lot of QR codes available while walking through slides, and you're not forced to scan that immediately, as the video would be available. And yeah, but that's the easiest way of sharing the information currently, I believe. Okay, so what is robotics? Well, in short, that's a study of robots, which covers the different phases like design, construction, operation, and the other stuff. Pretty similar to what we get used to in common development, software development, but this also covers the hardware part as well. On this video, you can see the current state of robotics. So of course, that's not everything that's happening in the robotics world at the moment, but you can easily find more videos on YouTube, and I will promise you you'll be excited from what you'll see. So robotics field is quite challenging, and there is a number of reasons for that. First of all, it could be easily put on the same line with such domains as healthcare, aerospace, automotive, etc. But because by definition, a robot assumes the significant interaction with the physical world, which also means interaction with human, of course. And technically, robots can be used in each of these areas. So the other reason is what I would like to highlight here is the price of the robot. So that's a commercial grade robot from Boston Dynamics. You probably heard about it before, called Spot. So and here is the price of the base version of this robot. Well, just to give you a comparison, here is the Porsche Cayenne price. Yeah, and as I mentioned, that's a base version, and well, if you want to make it more suitable for the for your business needs, you would need to add additional sensors like lidars, cameras, manipulators, and well, you may quickly end up with the price of Ferrari in this case. So you may just wonder, what do we get for this price? I would probably expect a perfect machine that can do everything we want, but in fact, it's imperfect. And well, we as an engineering team, we are responsible to make it safe for the surrounding environment and human. All right, and that's why testing is crucial. And if you talk to any robotics consultant, and ask if it makes sense to start testing on the real hardware, they would say no way. So because obviously the cost of the defect is huge, and that's why engineers in robotics, they start with simulation. They build simulated environment which is close to the real environment that the robot would operate in, and only after that they can move to the real hardware tests. I will cover this part a little bit later today, and now I'm gonna switch to the some common terminology, just to be on the same page, and it will help you to understand me better within this session. But you would also hear a lot of these terms in different robotic communities. So what is actuator? Well, to keep it simple, it's like a muscle of your robot, which makes the different parts of it move. And given this and that example with wheels, we can treat servo motors as actuators. Degrees of freedom, that's the level of flexibility and versatility of the robot. In this particular example, we can see a legged robot, so we can move its leg in different directions, and it is controlled by 3 servo motors. So usually in robotics community, it's common to treat the joints or actuators as a single degrees of freedom. So given each leg has 3 degrees of freedom, but the whole robot in total has 12 degrees of freedom. The pose of the robot is the combination of position and the orientation. So that's just a basic example of a cup in the 3D space, just to give you a reference. So we may have some point that represents its position, and probably the terms like yaw, pitch, and roll would be new to you, but basically they reflect the rotation angle along the corresponding axis. The easiest way to remember and to make a visual association with these terms is to follow this right-hand rule. Odometry, that's a very important process. Well, that's a method of robot's pose estimation. I will cover this part later within this session, but for now I would like to highlight that there is a number of ways how you can get this data, like Wilson encoders, visual distance sensors, and the other stuff. Velocity, that's something that you should be aware of from your school or university classes. I would just highlight here the difference. Well, the same way as we decompose the pose into position and orientation, here the linear velocity reflects the position change rate, and the angular velocity is about orientation. Joints and links, that's something you would hear a lot while modeling, on the modeling phase. Yeah, to give a visual association, we can refer to the human arm here. So basically each part of the arm might be treated as link, and the connections between these links are treated as joints. That might be wrist, elbow, shoulder, for example. And to compare it with industrial manipulator in this case, you can also see that there are a lot of links and joints as well. Kinematics, that's well, one of the most important and probably trickiest subfield in robotics. Well, technically it's an engineering branch of mechanics, and which in turn is a subfield of physics, but in short, it's a study of emotion. And let's probably consider the following example. You want to move your robot, or ask to move move your robot to the opposite side of the room. So in this case, we can decompose this task into robot positions change over time. So you need to move the robot from point A to point B. So we operate the robot's position in a 3D space or task space. But the robot itself, it knows nothing about the pose or 3D coordinates, so it doesn't care about it. So we need to tell the robots how well it should move to the opposite side of the room. And the only thing that the robot understands in this case is how to for instance, rotate the joints or servo motors, at which rate, what angle should we set for each joint. So that's about the joint space. So what kinematics does, given the pose of the robot, inverse kinematics allows us to transform this information into the joint angles of the robot, which makes all these servo motors work in a synergy, and that's what makes the robot's move realistic. And the forward kinematics is the opposite process. So given the joint angles, we transform this information into robot pose. Okay, so before we move on to the more technical stuff, I would like to touch the another important topic that would be like a brief overview of the autonomous systems. And the first thing I want to cover here are the variety of autonomy levels. So I don't want to cover them all. I would just focus on the boundaries to give you a reference. So the zero degree of autonomy is also known as a teleoperation process. That's assumed that we control our robot with a human in the loop. And we can technically use any known interface for that. For example, keyboard, mouse, gamepad, or even haptics. So that's an example, the most probably advanced example, how we can control robotic arms with special gloves, which mimic the human moves. And that's pretty useful in case if we want to operate in a potentially dangerous environment where for human. To give you an example of the full autonomy, the most popular one that you may find that probably would be a warehouse robot. But you may also heard about the autonomous vehicles, like self-driving cars that appeared on the market probably several years ago. That's also a good example of a fully autonomous system. In terms of capabilities, well, I already mentioned that robot assumed that the significant interaction with the physical world. So that's how it can collect the knowledge from the surrounding environment, the way how we human do that using our sensory, like eyes, arms, ears, and the other parts, right? So that's a sensing phase, and robot uses different sensors like lidars, cameras, inertial measurement units to collect this information. And we do that for some reason, of course, and that's how we come to the perception phase. That's where we know how to interpret this information. Given, for example, some visual sensors like camera, we can do, for example, objects tracking, or to be able to localize robot in the environment. We need to be able to estimate the pose of the robot. So that's just a couple of examples. Of course, it depends on the hardware that is mounted on the robot. When we know how to interpret this information, we can do planning, and that's where the business goals comes into play. Well, the basic example might be some patrolling stuff when you need to ask your robot to move through different waypoints around the territory and take some information. Yeah, and the acting phase, that's basically where we ensure that we follow our plan, and that's where we also close in the loop with the physical world. As soon as we send some commands to the robot, it changes the state of the environment, right? Okay, let's move on to the more technical stuff. If you ever wondered if there is anything existing which allows to control the robots, there is, and that's de facto standard called ROS, or Robotic Operating System. Just to clarify that that's not technically an operating system. We get used to like Linux, Windows, or Mac. That's more like a framework and a set of tools that allows us to effectively control the robots. There are two major versions at the moment. Well, technically, there are a lot of them, but I've just listed the recent ones. And the first version of ROS, it was originally developed 10 years ago. well, it was developed as a tool for researchers in robotics field, and yeah, you should realize that the age of this product applies some restriction, and it doesn't meet some requirements to the modern software and best practices. So that's why the ROS committee decided to, that one was one of the reasons why ROS committee decided to rewrite ROS. And that's how the second version appeared. Well, basically it addresses all the issues that are present in the first version, but you can read more about the differences between these two by scanning this QR code. Okay, so let's take a look at the common concepts. Well, I mentioned ROS2, but technically they are all valid for the first version as well. So what is Node? Well, Node is like a common process. It's just some sort of a wrapper, and you can put everything you want there. An example of the node might be a driver for some sensor, for example, or the planning and control nodes, to do the autonomous navigation. So everything else is pretty much about the way how these nodes communicates with each other. As technical, ROS is some sort of a communication-driven framework. So the topic-based communication is, well, if you ever worked with in IoT field, you may heard about MQTT protocols. So that's quite similar, but there are some differences, of course. The MQTT uses the broker to route requests between publishers and subscribers. ROS uses a bit different style that I will cover in a couple of minutes. But in terms of intention, the topic-based communication is designed to transfer different sensors data between nodes. The service-based communication is pretty similar to what you can see in the web development, probably. It is request-response based communication. The main intention here is short-term operations. For example, you may want to ask your robot to move the camera to a particular angle and take some screenshot. And as a response, you may get this screenshot for further processing. The action-based communication, similar to service-based, the intention is different here, as it is commonly used for long-running operations. For example, when we want to move the robot from point A from point B, that's an example of a long-running operation, and we cannot, in the real-world apps, we usually cannot predict how long would it take, especially if we operate in a dynamic environment with lots of obstacles and unpredictable environmental factors. So that's why we need some sort of feedback here. The example of the feedback might be like distance left to the target. And as a response, again, we can get a screenshot, for example, of the when we reach the target point. So moving back to the communication that is used by ROS. So ROS2 uses DDS, which stands for the data distribution services, and well, that's a popular communication way, and which is used in different fields like aerospace, healthcare, military, and the other stuff. Well, basically, it's a data-centric, highly performant, and secured standard that supports a rich set of quality of services with auto discovery and different types of communication. Imagine that, let's say you are building an autonomous vehicle and you want to, for example, know about everybody in 200 meters of you who is moving towards you at more than 2 meters per second speed. So that's my specification, and I want to get this information in a probably hundreds times per second rate. So I'm sending this info to all of my sensors. Well, at some point in the future, we can also send this data to rod cameras, for example. And all the external sensors will still write their data into local memory, but the DDS, which is running on the apps on the site, would perfectly know that we need this information. So it ensures, it guarantees that we will get it at a given rate. So that's why the DDS that's one of the reasons why DDS is preferable communication way in such apps. But there is a number of other reasons. In this schema, you can see the data flows from the autonomous vehicle, and there are lots of data sources. Just to give you an example, you may have like up to 16 cameras, different radar sliders, IMUs, and the other stuff. And the estimated bandwidth for such number of data flows, you may end up with up to 40 gigabits per second requirement. 40 gigabits, and that's huge. Even 5G doesn't allow us to do that. So yeah, that's probably all I want to cover related to DDS. You can read more by scanning this QR code. Just one thing that additional thing I want to highlight here is that ROS uses it as a middleware. It's like an interface, so it's a matter of changing the one environment variable to switch between different implementations. And there are commercial and open source version available on the market. So let's move to the common tasks and challenges that you may face during the common robotics development process. Of course, it's not the final list, and I just highlighted one of the most common. We will touch them only at high level, as each of these items might require a separate tech talk. So modeling is a very important process. I've already mentioned at the very beginning that there is a number of reasons why do we need to test our software in a simulation first. So that process covers the modeling of your robot. And the process itself is quite straightforward. There is a number of formats you can use. One of the most popular is URDF format. It's an XML-based format. There is also Xacra, which is more like a template engine, which allows you to create reusable blocks, define variables, macros, and the other stuff. So that makes your code more readable and maintainable. but at the end, this template engine would still generate your URDF, which is fed to the robot state publisher, that's a specialized node that interpreted this model and sent to all the potential subscribers. And an example of such subscribers could be visualization or simulation tools that need that information. So let's take a look at the example of a wheel. So here we have links and joins that I've already covered in the common terms section. So a wheel is our link, and the joint, well, basically it could be treated as a servo motor, but the only thing that I want to highlight here is the type of the joint. If we consider some rotary joint, that's like a servo motor, that's a continuum type and continuous type in terms of ROS specific modeling. And but you can also have like static joints. For example, if you want to connect some sensor like LiDAR or IMU to your robot body, they are not moving, so that would be a fixed type of the joint. The link consists of different parts. The visual parts use, well, it defines the geometry of different parts of your robot. It might be like some common shapes like cylinder boxes and the other stuff. But you can also use a 3D model here if you have experience of 3D modeling engineers in your team. You can create a fancy representation of your robot. Yeah, and the other part is about physics and dynamics. So that defines the collision geometry, which is used by simulation engines. In this particular case, as we describe a very simple robot, it is the same as the visual geometry, but sometimes you may it might be different. For example, if you want to restrict your parts from touching each other, or the other popular case, if you want to define the complex 3D model in the visual section, but to reduce computational effort, you can still use the simple geometry in the collision section. Inertia, that's a tricky one. I don't want to drill deep here into details, but it's about dynamics. That's a simple macros call in this case, but it covers, it encapsulates the definition of the rotational matrix, used by the simulation engines. So the joints, that's pretty straightforward, as in the joints section we define the relationship between different links. In our case, we have a robot base or like body, and we connect it with a wheel. We can also specify a relative position and orientation of this part here. So yeah, I've also mentioned that you can use the 3D model instead of common simple shapes. So that is achievable using the specialized 3D modeling tools like Blender. That's not quite the same robot, of course, but just to give you a reference, what can you create in this tool? Of course, if you need that. when you are done with the robot modeling part, you can switch to the environment modeling. And ideally that should be pretty close to the real environment that your robot would operate in. That's just an example of the room of one of the apartments that I've rented before. I spent about one and a half week with the zero knowledge in 3D modeling to build that. So technically, yeah, you can do the same. I would recommend the Polygon Runaway courses, Blender courses here. They have a free course, which basically would be enough to build something similar. Yeah, when you have both models, you can deploy them into simulation engine or physics engine. One of the most popular one is Gazebo. Well, here we can see our robot that I already described before. The world is a bit different. I've just reused an existing small house world. That's an open source world provided by Amazon. You can find it on the GitHub, and it would be pretty useful in case if you either don't have a real robot yet, or you want to practice some algorithms with your particular robot. So yeah, feel free to get more info about the Gazebo engine by scanning this QR code. Well, it is officially supported by the ROS committee and community. Sometimes people use different types of physics engines like Unity, but yeah, it's up to you what you will choose. But if you don't have any experience in robotics, I would recommend to stick with Gazebo. Okay, so that's an exciting moment because now I'm gonna share I want to show you the demo of the internal product that we are currently building at Waverly, Ukraine. And well, that's at this point, I want to also involve more people from different locations. So feel free to contact me either in Slack or, well, at the end you will see the feedback form where you can like leave your intention to assist with this project. Here I would like to say big thanks to the team that made that happen. You are awesome, folks. Yeah, and you can find this project on a GitHub. We've actually made it open source to involve the community as well. Okay, so let me switch to the different window. So here is the real app. The main screen here, it's pretty much like a video player you get used to in the other streaming apps. Well, at the moment it can stream, it allows us to stream video from the robot's camera. Below you can see the stream from my phone. Technically it's not a part of our app yet, but I wanted just to give you a reference to, from different, so that you can see the robot from different perspective. And the dog, well, we will use it for our experiments as well. Yeah, so basically at this point, this app allows us to do the teleoperation or remote control of our robot. We have different widgets here, like hardware sources. Battery is currently simulated. It's not yet implemented on the backend side, but memory and CPU are taken from the Raspberry Pi, used as a brain of our robot. robot speed is something very hardware specific. This particular robot works, its servo motors work at the top speed, so we cannot increase them. And technically, physically we cannot reduce them as well, but we can use some tricks, software tricks to make the motion slower. And additional actions are also robot specific. As it's a legit robot, we can move it up and down. The teleoperation part, the main point here is the main widget here is a keyboard widget, but we also can use a gamepad. At this point, the gamepad is still under development. In terms of the other hardware, as you can see on the real robot, it has a front camera. That's OGD light camera from Lexonis. It's a depth camera, so it can work in 2 modes. RGB mode is more like a common, pretty much like a common webcam stream, and depth mode, well, it would be easier to show you how it looks like on the demo. We can also enable AI specific stuff like object detection, and that's why we need a dock here. Okay, so let's probably, I will start the streaming process. We can see a dock from the front camera. Well, you can also check our hardware widget. There is a spike, so the CPU consumption is significantly increased, and that's where we're working to cap of these hardware capabilities. But anyway, the main advantage of this camera is that it allows us to do some heavy computations, like ML-driven computations on its own hardware. Okay, let's try to enable object detection mode. Okay, I guess you can hardly see the labels here. Unfortunately, I can't make it bigger as it is rendered on the backend side, but technically that's an overlay which focuses on the object that we have detected, and there is a dog label here, so our ML model successfully passed this test, but to be fair, it not always shows the similar results, as the model itself is not quite accurate. But anyway, technically we can use any model. So if we have enough data, we can retrain it. Yeah, and it also shows the confidence level here. Okay, so let's probably try to stand up. So you can see on the bottom screen that our robot is standing at the moment. Let me show you probably a couple of actions which we can do with the robot pose and some common movement operations. So let's say I want to move its head like this or this. So that's a very basic stuff. I can move it like this along its lead axis, right? So that's just the basic operations. We can move forward, backward. I want to be careful here as I'm operating on the table. There is not much space available here, and again, there is not. We haven't yet implemented some hardware or software restrictions, so we can technically easily break the robot. The way I have already shown the example, the battle of a spot and banana at the very beginning, so we can easily break our robot. Yeah, and let me switch to the depth mode. So we can't see anything yet. I will just turn the robot to my direction. You can see me sitting. Let me just move its head up. I can like move my head closer, turn it here like this. So that's a depth mode of the camera, which can also be used in the other tasks that we will cover later today, like obstacles detection. Okay, so that's how the teleoperation work. At the moment, that's pretty much we support in this app. But we have a roadmap, and well, technically we wanna add some more advanced stuff to be able to do autonomous navigation and robots fleet control and the other advanced stuff. Okay, so yeah, I would probably switch to our slides, and again I want to highlight, if you are interested and have capacity to participate in this project development, feel free to contact me, just fill in the feedback form at the end of the session. Okay, let's move on. So the other important task that is used in robotics is a localization. So that's basically an ability of the robot to know where it is in the environment. And this is a tricky one because it covers a lot of underlying algorithms involved. Basically, one of the most popular one is the sensor fusion algorithm, which allows us to merge data from different sensors to produce more accurate pose estimate. Well, you may just wonder, why do we need that? Why do we need to merge data from different sensors? Well, the reason for that is that our sensors usually lie. They are not so accurate as we might expect. They may produce noise, they might drift, they might be affected by the occlusions. So that's why we need to take an information that we really need from different sensors and feed it to the specialized algorithms that can do the magic and produce more accurate pose estimate. In this example, we can use wheels odometry and the IMU data. Specifically from the wheels odometry, we can take, for example, linear velocities, and from IMU we can take angular velocities. We can feed it to one of the most popular sensor fusion algorithm is well, it is technically the most simplest, but if you just trying to get started in robotics, you may probably use it at the first time. So yeah, the algorithm is called extended Kalman filter. So you can read more about it and the whole localization process by following this QR code. So let's move on. And the robot localization process is not usually done in isolation. So you usually use it in with mapping. And that's actually one of the most trickiest problem in robotics, called SLAM, or simultaneous localization and mapping. Well, from its definition, it seems quite simple and straightforward in the first glance, as you need to be able to localize a robot and build a map. But in fact, that is also associated. This problem is also associated with a chicken and the egg problem, because to build a map, you have to know where the robot is, and well, to be able to localize a robot in the environment, you need a map. Well, technically, to construct a map, you are taking different readings from different sensors like lidars, cameras, and so on. But the robot needs to know where it is in the world to be able to put this sensor data on the map, and to know where it is, we need a map to be able to align the current readings from the sensors with the previous data we received. So that's why we are reaching the circular dependency here, and that is also referred to the chicken and the egg paradox. Just give you a simple example of the 2D SLAM. Well, if you ever worked with the robot, vacuum cleaner robot, you may have already seen the companion apps like this that is displayed to the left. So first time when you run your robot, your vacuum cleaner, it examines your apartment, a house, and builds the map of your rooms. So that's a similar process here. Yeah, to the right you can see the 3D simulation of the small house using Gazebo, and that's where we use a lidar technically to build such stuff. You can even buy some inexpensive version which supports 360 degrees scans. Yeah, but more advanced robots, well, they commercial grade robot, they may use the more expensive lidars which supports 3D mapping. Yeah, you can, as always, you can read more about that by following this QR code. And that's an example of a 3D SLAM. So in case if you have an advanced cameras like Intel RailSense, it allows us to build such fancy 3D map, and that's also pretty common for the commercial grade projects. Okay, so let's move on to the autonomous navigation process. Technically, it's an ability of a robot to move from one one source to another, but without human intervention. So that's a very complicated process which involves all the data that we already learned from our previous slides. Just to summarize what information we need here. First of all, it's the ability of a robot to estimate the position. That's where we're getting this information from our SLAM algorithms. On the other hand, our robot should be aware of the obstacles to be able to navigate in autonomous manner, and that's where technically it's enough to have a static map that we also get from SLAM, but for the real robotic apps, when we operate in a dynamic environment with lots of obstacles, we may need live data, for example, from LiDAR sensors. And that's what allow us to build an additional overlay on the map, and it is called cost map. So basically, given the 2D map example that I've already shown you before, we can decompose it, subdivide it into a grid of cells, and each cell can be assigned with a cost depending on the whether there is obstacle or not in this particular cell. So yeah, that's well, that's the basic explanation, but in fact, that's a very complicated process. And when you first take a look at the specialized software that allows you to do that, you will be a little bit surprised and shocked to see the 500 lines configs to do this stuff effectively. And sometimes people spend months to fine-tune all these algorithms to be able to move your robot and avoid obstacles, goes into some narrow places, and other stuff. So let's take a look at the how what this process looks like in simulation. Here is the same robot. To the left, you can see the 2D version. The robot moves fully autonomously around the sofa through a given set of waypoints. It's like a patrolling task. And on the same hand, we see the additional overlays or cost maps rendered here, which allows us to track the potential obstacles. To make the experiment more realistic, the human model was deployed here as well. Well, that's a very interesting case in terms of testing, especially if your robot assumes the real interaction with human, as obviously we can't predict how some person would react when it meets a robot. In this case, the human is pretty neutral. It just tries to omit any contact with the robot, but we can also simulate the other behaviors like aggression, fenciness, and other stuff. Okay, so that's pretty much I wanted to cover related to common tasks, and I want to give you like a quick start checklist. As you may already guessed, it's not really quick, but anyway, it should help you to get familiar with this domain. If you haven't worked with this before, I would probably recommend you to look at the relative areas like IoT. You can buy relatively inexpensive microcontrollers like ESP32, Arduino, even Raspberry Pi. Connect some sensors, and it will give you some basic understanding how does all those stuffs work. To look at the data flows, you can even control servo motors there. So yeah, that's just the basic stuff. Then you can switch to the more robotics oriented stuff, and I prepared a list of some very basic inexpensive robot that you can either build on your own if you if you have a 3D printer or buy, to be able to build more advanced stuff, you can, well, the starting price would be like from $300, and the robot you see on the demo, it's a mini pepper. By the way, there is a second version of it available on the Kickstarter, so you can order that robot. Well, that's where you can play with the ROS, with sensors that are pretty common for the commercial grade robots, like LiDAR cameras. The main difference would be probably in the type of a robot. If you wish to play with a wheeled or ledged or even aerial robots, the brain could be, the most popular versions are the Raspberry Pi and Jetson boards. So products supplied by NVIDIA, that they use Jetson boards, and the main advantages in this case would be the GPU capabilities. So in case if you want to do some AI related stuff, it would be the best option for you. So yeah, at some point you would definitely need to drill into the some Linux basics and some programming languages. Rust, well, it officially supports C++ and Python. Python obviously is easier to learn. Well, technically the second version was completely rewritten, I mean Rust, and it allows you to run to write new clients in different languages. But anyway, Python, C++ has better support in the moment. And in terms of ROS basics, you can even follow the official documentation here, and I would also recommend you to use to read a book, which is currently at the early access. Robotics for engineers, and it will give you different basics about underlying math and physics. And the last one, and well, if you want to play with more with to get more practical experience, you can try live projects. I personally paused a series of Rust 2 for mobile robots projects, but that's more like an advanced level. It requires some programming experience, Git knowledge, and the other stuff, which is pretty common for the development. Well, yeah, but even if you don't have experience in robotics, that should be, you can give it a try. And well, you will basically cover in live projects, you will basically cover all the topics that we have discussed in this session. Okay, so that's pretty much it I wanted to cover within this session. Feel free to scan this QR code, which will lead you to the feedback form, and I would be greatly appreciated to get it. And actually, if you are interested to participate in the project that I have done today, well, yeah, feel free to pin me in Slack. Well, I see we are ran out of time, and I propose to move the questions to our All Robotics Slack channel. So it is public, so everyone can join. Okay, so that's pretty much it. Thanks everyone for joining, and have a great end of the day and the weekend.